My name is Jim Al-Khalili. I'm a professional physicist, and I've been making films about my passionate interest in science for many years. I never cease to be astonished at the awesome power of science in shedding light on everything in the universe, from the tiniest things in existence to extraordinary objects on a cosmological scale. In this series, I want to show you how science gives us insights into the biggest questions of all. How did the universe come into being? How did life start on Earth? And how does it sustain itself? What is the nature of space and time, the very reality we live in? And how will it all end? In this episode, we'll look at the first two great pillars of modern physics: Einstein's general theory of relativity, which has radically transformed our understanding of space and time, and quantum mechanics, which reveals the mind-blowingly strange world of the subatomic. And we'll see how the quest to unite the two theories into a theory of everything has given rise to some extraordinary ideas about the fundamental nature of reality. I want to explore the latest developments and astonishing new theories that continue to shape the way we understand the universe. I hope this series will show you just how amazing our universe is. Our story starts with a question. It may never have occurred to you to ask, but once you start looking into this question, the horizons it opens up are mind-boggling.
Okay, so what is space? But does space only exist when there's stuff in it? Does space only have a meaning when it's enclosed by walls? Ultimately, the question is this: does space in itself have form?
The properties of space were first described by the mathematician Euclid over 2,000 years ago in his legendary text, The Elements. In it, he laid down a set of simple logical rules about space in what today we call Euclidean geometry.
For Euclid himself, and for almost all mathematicians for the next 2,000 years, these rules weren't just true mathematically. They were also true statements about physical reality itself. So they thought that two parallel lines would remain parallel forever, that a triangle in real space would always have angles adding up to 180 degrees. But, weird as though this might sound, it's not actually always true.
Almost 250 years ago, in a small town in northern Germany, a mathematician was born. His name was Carl Friedrich Gauss. Gauss tackled many great problems in his career, but from a young age, he began to speculate that the rules of Euclid may not be as absolute as everyone had assumed. For example, on the surface of a sphere, the angles of a triangle can add up to more than 180 degrees.
Let me explain with this globe. You see, we can see that it's three-dimensional because we can stand back and look at it. But what if you were an ant stuck on the surface? How would it know that that surface is curved? So imagine you're the ant and you start off at the North Pole, and facing south, you move down towards the equator. At the equator, you still face south and you shuffle sideways along the equator. Then you reach a certain point, and then you start walking backwards, so you're still facing in the same direction, and head back to the North Pole. Now, look what's happened here. You've been pointing south all the way round, and yet when you arrive back at your starting point, you're facing in a different direction. Understanding this gives us a way of calculating the curvature of a surface without ever leaving it.
This was an amazing insight, but it only applies to curved surfaces, which are two-dimensional. It would take a brilliant student of Gauss's, Bernhard Riemann, to develop these ideas in a way that could be applied to the three-dimensional space that surrounds us. Aged just 26, Riemann encapsulated his strange new ideas about geometry in a lecture that was to become legendary among mathematicians.
In June 1854, Riemann delivered his lectures to an enraptured audience. In them, he detailed how he'd taken Gauss's ideas on curved surfaces and generalized them, so that they applied not only to curved two-dimensional surfaces, but the curvature of space in any dimension. Okay, so I'm sure this all sounds rather complicated. What exactly do we mean by curved space in any dimension? So let me try and explain. Here's the thing, Gauss talked about curved two-dimensional surfaces. Well, here we have a sheet of paper, and it's two-dimensional. So if I curve it, we can visualize and see this curvature, but only because it's embedded in 3 dimensions. Now, what if we curved 3 dimensions? Presumably, we'd need a 4th dimension.
But how do you get to this 4-dimensional space? It's impossible to step outside of our 3-dimensional world. Wherever you travel in the universe, no matter how far you go, you're always stuck in 3 dimensions. The genius of Riemann was to show that you didn't need to stand in a 4th dimension to tell if space was curved. You could actually do it from the inside. But for Riemann, this would always remain a purely mathematical idea. It would take Albert Einstein to tie these mathematical ideas together and apply bendy, curved, non-Euclidean geometries to the real space that surrounds us.
In the general theory of relativity, Einstein took the mathematics of Gauss and Riemann and used it to paint a revolutionary picture of the physical world. He showed that, just as Gauss had suspected, the geometry of the space around us isn't always of the regular, flat Euclidean kind.
But if space is bent and warped all around us, surely we must be able to observe that this is the case. Well, we do, just not in the way you might expect. This was Einstein's major insight. He showed that it was the ability for space to bend and warp, for it to be flexible and change its geometry, that gives rise to the force we call gravity.
Now, since Newton's time, gravity was thought to be a force that pulls all objects together. So if I drop this apple, it's as though there's an invisible rubber band that's pulling it down towards the Earth. But Einstein's general theory of relativity gives us a completely different picture and a totally new perspective. So although gravity appears to be a force, it's nothing more than the curvature of space itself. When an object falls, it's not being pulled by gravity at all. It's just following the simplest path through bent space.
But the equations of general relativity didn't end there. They revealed that it was the presence of mass that caused space to curve and distort. The reason we have gravity on Earth is because the Earth is actually bending the space around it. And although we don't perceive it like this, Einstein showed us that we live in a four-dimensional universe. The fourth dimension is time. The onward flow of time itself is also warped by gravity, just as much as the other three dimensions of space.
Gauss, Riemann and Einstein had between them come up with a description of how the space and time we exist in can be warped. They showed that space and time are not the fixed, unchanging stage on which the actions of the universe are played out. They're actually part of the performance.
Einstein's equations were also describing a universe that was expanding. Physicists found it hard to believe at first, but astronomical observations soon told them it was absolutely true.
But, and this is the crucial point here, it's not that the galaxies are flying away from each other through space, but rather that the fabric of space itself, in between the galaxies, is expanding. So the universe in its entirety is getting bigger.
And that led to an inescapable conclusion. If the fabric of space is expanding, then if you wind the clock far enough backwards, there must have been a moment of creation. The universe began with all of its energy squeezed into a singularity, a point of infinite density and gravity. From this earliest moment, space expanded rapidly, spreading matter and energy as it grew, to eventually create our vast universe. This event is known as the Big Bang. Radio telescopes have since been able to detect it, because the heat left over from that extraordinary initial moment turned into electromagnetic radiation, which fills all space. This is a memento, the fossilized light of the first dawn.
For me, Einstein's general theory of relativity is the first great pillar of modern physics. It's led to some extraordinary insights into the nature of the universe, from the Big Bang to black holes. But if we want to understand the world at the tiniest scales, then we need to wrap our heads around the second great pillar of physics. And that's an area of science that I've spent my life studying.
If you thought curving space and time is weird, you've heard nothing yet. Get ready for the impossible world of quantum mechanics.
To paraphrase one of the founders of quantum mechanics, everything we call real is made up of things that cannot be themselves regarded as real. And at stake, that everything we thought we knew about the world might turn out to be completely wrong.
We're going to start this journey into scientific madness by asking another fundamental question of physics. What is light? Well, you've probably heard of light waves, so perhaps you might imagine that light is a wave. Understandably, that's what many scientists thought too, in the age before quantum mechanics. It seemed perfectly reasonable. All around us, we see light behaving in a perfectly common-sense, wavy way. Look at the shadow of my hand. It's fuzzy around the edges. We understand this as the light hitting the sides of my hand and bending and smearing out slightly, just like water waves around an obstruction. Perfectly common-sense, wave-like behavior. Rather like ripples on the surface of water, light was simply ripples of energy spreading through space. And this was as firmly accepted as the fact that the Earth was round. But was this always true? Bit by bit, troubling evidence emerged that seemed to contradict the received opinion. In the late 19th century, scientists were studying the then newly discovered radio waves and how they were transmitted. And to do that, they were building experimental rigs very similar to this one. Basically, by spinning this disk, they could generate huge voltages that caused sparks to jump across the gap between the two metal spheres. But in doing so, they discovered something very unexpected to do with light. They found that by shining a powerful light source on the spheres, they could make the sparks jump across more easily. This suggested a mysterious and unexplained connection between light and electricity. To understand what was happening, scientists used this. It's called a gold leaf electroscope. It's basically a more sensitive version of the spark gap apparatus. Now, first of all, I have to charge it up. What I'm doing is adding an excess of electrons that are pushing the two gold leaves apart. Now, first I take red light and shine it on the metal surface, and nothing happens. Even if I increase the brightness of the light, still the gold leaves aren't affected. Now I'll try this special blue light, rich in ultraviolet. Immediately, the gold leaves collapse. Light can clearly remove static electric charge from the leaves. It can somehow knock out the electrons I added to them. But why is ultraviolet light so much better at doing this than red light? This new puzzle became known as the photoelectric effect. It was a big problem for physicists. And it may not surprise you to learn that, once again, it was Albert Einstein who provided the answer. This is the Achenhold-Sternwarte Observatory in Berlin. Perched on top is a strange, huge iron and steel construction. But it's not a gun. It's actually a telescope. Built in 1896, the telescope was one of the largest of its kind in the world and made the observatory the go-to place to engage and astound the public in new science. Albert Einstein gave a very famous public lecture here on his theory of relativity, which is, of course, what he's most famous for. But it's not the work that won him the Nobel Prize. In 1905, he'd also come up with a new theory to explain the photoelectric effect. And what he suggested was revolutionary and even heretical. He argued that we have to forget all about the idea that light is a wave and think of it instead as a stream of tiny bullet-like particles. The term he used to describe a particle of light was a quantum.
I'll try to explain how this helps using a rough analogy. Of course, like all analogies, it's far from perfect, but hopefully it'll give you a sense of the physics to help you understand why thinking of light as a stream of particles solves the mystery of the photoelectric effect. In this analogy, these red balls represent Einstein's light quanta.
And those cans over there are the electricity held in the metal.
Now, in the original experiment, they made electricity flow from the surface of the metal by shining light on it. In my analogy, I'm going to try and knock those tin cans over using these red balls.
Absolutely no effect. That's just like red light. According to Einstein, each particle of red light carries very little energy because red light has a low frequency. So even a very bright red light with many red light particles can't dislodge any electrons from the metal plate, just like the red balls.
Now I'm going to use heavier balls, like these blue golf balls, and I'm going to try and knock off the tin cans with these.
They're like the ultraviolet light in the experiment. Now, each individual light particle carries more energy because ultraviolet light is higher frequency. Just a few of them, like a dim ultraviolet light, are enough to knock the electrons out of the metal plate and collapse the gold leaf.
So Einstein's idea that light is made up of tiny particles or quanta is a wonderful explanation of the photoelectric effect. I remember when I first learnt about this, being blown away by its sheer elegance and simplicity.
Okay, so was Einstein right? Light is made up of tiny bullet-like particles. Well, yes and no. Fast forward past the First World War to the Roaring '20s, and another experiment which yet again bamboozled the world of physics. It's the birth of modernism, a time of cultural revolution and scientific revolution too. Most mind-boggling of all is an extraordinary experiment which challenged the very basis of reality itself. But weirdly, it was an experiment that wasn't even about light. It was about the particles that make electricity.
In the mid-1920s, an experiment was carried out at Bell Laboratories in New Jersey in America, which uncovered something entirely unexpected about electrons. Now, at the time, it was accepted without question that electrons were these tiny lumps of matter, small but solid particles like miniature billiard balls. In the experiment, they fired a beam of electrons at a crystal and watched how they scattered. Now, that's entirely equivalent to taking a beam of electrons, say, from an electron gun, and firing it at a screen with two slits in it, so that the electrons pass through the slits and hit another screen at the back.
What the Bell scientists found shocked the physics world to the core. To understand why, consider a similar experiment with water waves.
I've set up a simple experiment. I have a water ripple tank placed on top of an overhead projector. I have a generator producing waves that pass through two narrow gaps. The projector beams the image of the waves onto the back wall. You can see as the waves come in from the left and squeeze through the two gaps, they spread out on the other side and interfere with each other. What this means is that when you get the crest from one wave meeting the crest from another, they add up to make a higher wave. But when the crest from one meets a trough, they cancel out. This gives rise to these characteristic lines leading to the signature wave pattern.
Bands of light and dark. Whenever you see these light and dark bands, the signature wave pattern, you know without doubt that you've got wave-like behavior. So, guess what they saw in New Jersey?
Now it seemed that firing electrons, tiny solid particles, through the two gaps produced exactly the same kind of pattern, bands of light and dark. First, light, for a long time believed to be a wave, was found to sometimes behave like particles. And now electrons, for a long time believed to be particles, were behaving like waves.
But it was actually stranger than that. The wave pattern wasn't merely some result of the entire beam of electrons.
More recently, this experiment has been repeated in labs around the world by firing one electron at a time through the slits onto the screen.
At first, each electron seems to land randomly on the screen. But gradually, a pattern forms. The signature wave pattern.
Let me be quite clear about just how weird this is. Remember from the wave tank experiment where the signature wave pattern only exists because each wave passes through both slits and then its two pieces interfere with each other. But here, every individual electron, each single particle, is passing alone through the slits before it hits the screen.
And yet, each single electron is still contributing to the signature wave pattern.
Each electron has to be behaving like a wave.
One of the leading exponents of the new science of quantum mechanics was Niels Bohr. He and his colleagues built a new theory of light and matter, and they just decided to put up with how mind-bendingly strange it was.
As Niels Bohr himself said, anyone who isn't shocked by quantum theory hasn't understood it. So, viewers, I'm going to take our tiny electron and use it to delve deep into the heart of reality. And yes, prepare to be shocked, because this is the only way to explain what we observe when a single electron travels through the slits and hits the screen.
Quantum mechanics says this: we can't describe what's traveling as a physical object. All we can talk about are the chances of where the electron might be. This wave of chance somehow travels through both slits, producing interference just like the water wave. Then, when it hits the screen, what was just the ghostly possibility of an electron mysteriously becomes real.
Let me try and capture just how weird this is with an analogy. If I spin this coin, then all the time it's spinning, it's a blur. I can't tell if it's heads or tails. But if I stop it, I force it to decide, and it's heads. So before, it was sort of not heads or tails, but a mixture of both. But as soon as I've stopped it, I've forced it to make up its mind. This is what Bohr and his supporters claimed was happening with our electrons.
In a sense, as it spins, the coin is both heads and tails. Similarly, the electron's wave of chance passes through both slits, two paths at the same time. Our coin then stops at heads. The ethereal wave of probability hits the screen and only then becomes a particle. The quantum world was unlike anything ever seen before.
It's hard to overstate just how crazy this is. Bohr was effectively claiming that one can never know where the electron actually is at all until you measure it. And it's not just that you don't know where the electron is. It's weirdly as though the electron itself is everywhere at once. Bear in mind that electrons are among the commonest and most basic building blocks of reality. And yet, here's Bohr saying that only by looking do we actually conjure their position into existence. It's like there's a curtain between us and the quantum world, and behind it, there is no solid reality, just the potential for reality. Things only become real when we pull back the curtain and look. And this view, ladies and gentlemen, became known as the Copenhagen interpretation.
None of it seemed to make any sense. Yet it was proven true in experiment after experiment. So most scientists shrugged aside the philosophical problems and got on with harnessing the incredible power of this new science.
It simply didn't matter to them because it worked. They even coined a phrase for it: shut up and calculate.
Quantum mechanics led to a profound understanding of semiconductors, which helped create the modern electronic age. It produced lasers, revolutionizing communications, breathtaking new medical advances, and breakthroughs in nuclear power. Still to this day, quantum mechanics remains a mystery we simply have to accept. It tells us that on the subatomic scale, there's no such thing as empty space, even in a vacuum. Particles are continually popping into existence and almost immediately cancelling themselves out. Space is seething with them, appearing and disappearing. And it's thrown up an even crazier sounding phenomenon which seems to defy some of the most sacred laws of physics. It's known as entanglement.
Now, entanglement is this special, incredibly close relationship between a pair of quantum particles whose fates are intertwined. For example, if they were created in the same event. Let me try and explain this by imagining the two particles are spinning coins.
Imagine these coins are two electrons, created from the same event and then moved apart from each other. Quantum mechanics says that because they're created together, they're entangled. And now many of their properties are forever linked, wherever they are.
Remember, the Copenhagen interpretation says that until you measure one of the coins, neither of them is heads or tails. In fact, heads and tails don't even exist. And here's where entanglement makes this weird situation even weirder.
When we stop the first coin and it becomes heads, because the coins are linked through entanglement, the second coin will simultaneously become tails.
And here's the crucial thing. I can't predict what the outcome of my measurement will be, only that they will always be opposite.
That was almost too crazy to imagine.
It's as if the two coins are secretly communicating instantaneously across space and time, even if the first coin was on Earth and the other was on Pluto.
Entanglement may drive the next technological revolution. It underpins quantum computers, machines that could solve problems which are far beyond the reach of the fastest machines that we build today. And yet it remains a mystery, because the laws of physics say that nothing can travel instantaneously across space. So how can these particles possibly be entangled with each other? It's something we still don't fully understand.
ever since the two theories were developed around a century ago, scientists have suspected that quantum mechanics and Einstein's general theory of relativity were really just two sides of the same coin. Now, both theories describe our reality, but on very different scales. Quantum mechanics down at the subatomic and general relativity at the cosmic scale. So now the quest is underway to try and unify these two theories, to find a so-called theory of everything.
In recent years, an astonishing idea has been gaining ground with many theoretical physicists, which may possibly crack that problem. The idea came out of the study of those extraordinary objects in outer space, black holes. When a massive star collapses on itself, it gets smaller and smaller until it heads towards a singularity, a point of infinite density and infinite gravity. It's a weird structure composed of massively warped space and time. It's by studying black holes that physicists have been pursuing one of the biggest questions of all. What is space and time?
If you've watched my films before, you probably won't be surprised to see that I've decided to represent the awesome majesty and sheer destructive power of a black hole with a water slide and a rubber duck.
My poor little duck is about to fall into the black hole. And while it's not, of course, a literal analogy, if you can imagine the water in the slide represents space and time, I'm hoping my homemade contraption will at least give you an inkling of just how mysterious a black hole really is.
Now, imagine that's the black hole over there, the swimming pool, and this is the unfortunate duck that's been caught by its immensely powerful gravitational field, and so will be pulled inexorably towards it. The big question is, what will happen to the duck as it approaches the black hole?
Now remember, Einstein realized that space and time aren't fixed or stable. They change according to your perspective and factors such as the speed you're traveling and the distortions of the gravity you're in. From the perspective of the duck, things will seem normal as it moves towards its inevitable extinction in the jaws of the black hole. At least that's what happens from its perspective.
But Einstein's general theory of relativity tells us that, from my perspective, something very strange indeed appears to happen.
So let's see exactly the same event again, but from my perspective. Because the duck is moving into stronger and stronger gravity, the space around it will distort more and more. The duck will mysteriously seem to get slower and slower and slower, from my perspective. Eventually, the duck will reach a point of no return. It's called the event horizon, and it's a place where gravity is now so strong that nothing, not even light, can escape. For me, it will seem as if the duck has frozen exactly at the horizon. General relativity says the duck will fall into the black hole, but I will never know, because it's impossible to see beyond the event horizon. And that's one reason why black holes are so mysterious.
Now, we can't be absolutely certain what would happen to the duck after it falls into the black hole, but it's a pretty safe bet that at some point the gravitational stresses inside the black hole are going to rip the duck apart. Now, let's take a different duck. In this case, a rather tasteful looking ceramic one. And I want to use it to demonstrate a very important idea in physics. But to do that, I'm going to need safety goggles and a hammer. I'm sorry, but that felt rather good. But I think we can agree that you'd be very hard pressed to put this duck back together again. But it's a very important principle in physics that, in theory, we should be able to reconstruct anything, even if it has been smashed to smithereens.
So even if the duck has fallen into the black hole and been destroyed, the record of it, the information which could put it all back together again, should never be lost from our universe. But this leads us to a major paradox which is still unsolved.
So we know that even if the duck falls into the black hole, the information that describes it can't be lost. But, and this was something discovered by Stephen Hawking, black holes have a temperature. They give off radiation. And if you leave them long enough, they'll just evaporate away. But now we have a really big problem. Where has the duck's information gone now?
All right.
Some of the world's leading theoretical physicists are wrestling with this very problem.
Hello. Hi, how are you?
Because it could have enormous consequences for our understanding of reality itself. Physicists such as Professor Sean Carroll.
If we want to talk about the black hole information puzzle at all, it's only a puzzle if you know the black holes evaporate. Because if black holes don't evaporate, then you can just say, the information's not gone, it's in the black hole. It's only when you say the black hole evaporates and it evaporates into featureless radiation that the information seems to be lost. So this is a puzzle. This is the real heart of the black hole information loss puzzle.
The paradox has led some physicists to an extraordinary suggestion. Although the duck falls into the black hole, what if its information somehow stays on the event horizon, in the same way as the duck seems to freeze to the outside observer? Professor Marika Taylor has spent years theorizing how this seemingly impossible concept might actually be true.
It turns out that the surface of a black hole really doesn't behave in the way that we would expect it from everyday life. So there are really strong quantum effects around a black hole horizon. And then as you throw something into a black hole, it might be absorbed in this complicated kind of quantum computer state. So you can kind of think here of something like in the Matrix movie, you know, some really complicated quantum physics going on. The information is kind of trapped there.
It seems that there is very, very good reason to believe that whatever information is inside the black hole can, in the appropriate senses, be thought of as living on the surface of the black hole.
To help us conceptualize this extraordinary idea, physicists refer us to a technology which exists right now. It's not an exact analogy, but it helps us understand the basic idea at the heart of it all. This new theory of reality is known as the holographic principle. The reason it's called the holographic principle is because a hologram generates a realistic-looking three-dimensional image, but all the information needed to describe the hologram is contained on a two-dimensional surface. Now, the next step in our story is quite extraordinary, because some physicists have extended the idea of a hologram to explain the entirety of our universe. So it could be that the holographic principle could describe the fundamental nature of everything.
So holography is the idea that the whole of our universe could really be understood in terms of something which lives in 2 dimensions. That's why people call it holography.
The idea is that somehow what you and I think of as the real, tangible, 3-dimensional world is encoded on a 2-dimensional surface. All the information there is located on that 2-dimensional surface.
Professor Juan Maldacena is a world-leading physicist who's developed the idea of the holographic principle.
So the idea is that everything that is happening in our 3-dimensional world is really encoded on the 2-dimensional boundary, so some region very far away. It's like having a crystal ball, but the ball is very big at the edge of the universe. And yeah, so what's happening in the interior and what's happening in the boundary are 2 alternative descriptions of the same reality. And the physical laws, the fundamental physical laws on the boundary are simple, but they create a complex quantum state.
When Maldacena first was giving talks in 97, 98, some of the reactions are, look, this has to be crazy, right? And it was only when he really started to flesh out the calculations, show how it worked mathematically, within 6 months or so, that the entire community was convinced by it.
After the initial skepticism, thousands of physicists around the world are now working on the holographic principle as a possible explanation for physical reality itself. This is a theory that could bring together the quantum world and the universe as described by general relativity into one all-encompassing theory of everything.
Now, it's important to say that no one has yet proved that we're all holograms. That's still theoretical speculation at the moment. But the mind-boggling concept, taken seriously by a lot of physicists, is that all the information needed to describe our 3-dimensional space could be stored in a quantum state on a 2-dimensional boundary at the edge of the universe. Now, that's quite something to get your head around.
We're still, in some sense, absorbing the paradigm shift, the philosophical consequences of this, because it is something very profound to say that really, the 3-dimensional reality that we think we live in is deceptive, that when we get to the true quantum level, that actually there's a fundamental 2-dimensional world. We need to understand this concept more. And we also need to see how we're going to see signals of this in our astrophysical data, in our cosmological data, in data that we get from particle colliders such as CERN. And I think by the end of this century, we'll look back at the beginning of the century and just be astonished about the way our perceptions of physical reality have actually changed.
Well, it's certainly not proven yet. But perhaps in 10 years' time, I'll make another film in which I tell you that, yes, it's been proven we are all holograms. Or maybe there's another mind-boggling theory, a whole new way of looking at reality that's waiting round the corner to be discovered.
My name is Jim Al-Khalili. I'm a professional physicist, and I've been making films about my passionate interest in science for many years. I never cease to be astonished at the awesome power of science in shedding light on everything in the universe, from the tiniest things in existence to extraordinary objects on a cosmological scale. In this series, I want to show you how science gives us insights into the biggest questions of all.
How did the universe come into being? How did life start on Earth? And how does it sustain itself? What is the nature of space and time, the very reality we live in? And how will it all end?
In this episode, I want to look at the astonishing amount that physics can now tell us about the natural world we see all around us. We'll investigate some deceptively simple laws of physics which explain how life itself can exist and thrive in the universe. We'll learn how exquisite patterns of nature can emerge spontaneously from simple mathematical rules. I'll show you how my own research into the spooky world of quantum mechanics may help us understand some of the most important processes in life. And we'll tackle one of the biggest mysteries of all. How did life begin? I want to explore the latest developments and astonishing new theories that continue to shape the way we understand the universe. I hope this series will show you just how amazing our universe is. I'm going to start this episode by looking at one of the fundamental pillars of physics: the laws of thermodynamics. As unlikely as it sounds, it was steam engines which led to the discovery of these beautiful, simple laws. By the first half of the 19th century, steam technology was transforming human societies with bewildering speed. But although these engines clearly worked in practice, no one really understood the physics behind them. It took a brilliant French scientist working in the aftermath of the Napoleonic Wars to crack the problem. His name was Sadi Carnot. What really bothered Carnot was the technological superiority that France's enemies seemed to possess. So Carnot vowed to really try and understand how steam engines work and use that knowledge for the benefit of France. Carnot saw that all heat engines comprised of a hot source in cooler surroundings. Now, Carnot believed that heat was some kind of substance that would flow like water from the hot to the cool. And just like water falling from a height, the flow of heat could be tapped to do useful work. Carnot's crucial insight was to show that to make any heat engine more efficient, all you had to do was to increase the difference in temperature between the heat source and the cooler surroundings. Carnot had revealed that heat engines weren't just a clever invention. They were tapping into a deeper property of nature. They were exploiting the flow of energy between hot and cold. But as the 19th century progressed, the study of heat, motion, and energy began to grip the wider scientific community. Soon, it was realized that these ideas could do much more than simply explain how heat engines worked. These ideas were applicable on a much grander scale. By the mid-19th century, scientists and engineers had worked out very precisely how different forms of energy relate to each other. They measured how much of a particular kind of energy is needed to make a certain amount of a different kind. Let me give you an example. The amount of energy needed to heat 30 milliliters of water by 1 degree centigrade is the same as the amount of energy needed to lift this 12.5 kilogram weight by 1 meter. The deeper point here that people realized was that although mechanical work and heat may seem very different,
They are, in fact, both facets of the same thing: energy.
This idea would come to be known as the first law of thermodynamics. The first law reveals that energy is never created or destroyed. It just changes from one form to another. 19th century scientists realized this meant the total energy of the entire universe is actually fixed. Amazingly, there's a set amount of energy that just changes into many different forms. So, in a steam engine, energy isn't created. It's just changed from heat into mechanical work.
But impressive though the first law is, it begged an enormous question. What exactly is going on when one form of energy changes into another? In fact, why does it do it at all?
The answer would in part be found by German scientist Rudolf Clausius, and it would form the basis of what would become known as the second law of thermodynamics. Clausius realized that not only was there a fixed amount of energy in the universe, but that the energy seemed to be following a very strict rule. Put simply, energy in the form of heat always moved in one particular direction.
This insight of his is in fact one of the most important ideas in the whole of science. As Clausius put it, heat cannot of itself pass from a colder to a hotter body. This is a very intuitive idea. If left alone, this hot mug of tea will always cool down. What this means is that heat will pass from the hot mug, say, to my hand, and then again from my hand to my chest.
This might seem completely obvious, but it was a crucial insight. The flow of heat was a one-way process that seemed to be built very fundamentally into the workings of the entire universe. Left alone, energy seems to always go from being concentrated to being dispersed.
Clausius brought together all these ideas about how energy is transferred and put them into mathematical context. It can be summarized by this equation. Now, what Clausius did was introduce a new quantity he called entropy, this letter S. Basically, what it's saying in the context of this equation is that as heat is transferred from hotter to colder bodies, entropy always increases.
It appeared to Clausius that in any isolated system, this process would be irreversible.
Clausius was so confident about his mathematics that he figured out that this irreversible process was going on out there in the wider cosmos. He speculated that the entropy of the entire universe had to be increasing towards a maximum, and that there was nothing we could do to avoid this. This idea became known as the second law of thermodynamics.
The second law of thermodynamics seemed to say that all things that gave off heat were in some way connected together. All things that gave off heat were part of an irreversible process that was happening everywhere. A process of spreading out and dispersing. A process of increasing entropy. The second law says the universe itself must one day reach a point of maximum entropy, maximum disorder. The universe itself must one day die. If everything degrades, if everything becomes disordered, you might be wondering how it is that we exist. Contrary to what you might think, it's precisely because of the second law that all this exists. The great disordering of the cosmos gives rise to its complexity.
It's possible to harness this natural flow from order to disorder, to tap into the process and generate something new, to create new order, new structure. The engine of my car, like all engines, is designed to exploit the second law. It starts out with something nice and ordered, like this petrol, stuffed full of energy. But when it's ignited in the engine, it turns this compact liquid into a mixture of gases 2,000 times greater in volume, not to mention dumping heat and sound into the environment. It's turning order into disorder. What's so spectacularly clever about my car is that it can harness that dissipating energy. It can siphon off a small bit of it and use it for a more ordered process, like driving the pistons which turn the wheels. That's what engines do. They tap into that flow from order to disorder and do something useful. But it's not just cars. Evolution has designed our bodies to work thanks to the very same principle. If I eat this chocolate bar packed full of nice, ordered energy, my body processes it and turns it into more disordered energy, but powers itself off the proceeds.
Steam engines, power stations, life on Earth. All of these things harness the cosmic flow from order to disorder. But the laws of thermodynamics alone aren't enough to explain why there's so much complexity in our world, such intricate and apparently ordered structure. Ours is a world where inanimate matter spontaneously creates exquisite beauty, where a chaotic and unpredictable universe has turned simple dust into human beings. It's even more amazing when you consider that we ourselves are made up of just a handful of simple elements.
These are the elements and compounds from which all humans are made. They're incredibly, almost embarrassingly common. In fact, almost 99% of the human body is a mixture of air, water, coal, and chalk, with traces of other slightly more exotic elements like iron, zinc, phosphorus, and sulfur.
In fact, I've estimated that the elements which make up the average human cost at most a few pounds. But somehow, trillions of these very ordinary atoms conspire miraculously to organize themselves into thinking, breathing, living human beings. How the wonders of creation are assembled from such simple building blocks is surely the most intriguing question we can ask. The answer lies in the extraordinary world of chaos theory. Before the coming of chaos theory, scientists had a pretty fixed idea of how everything in the universe worked. In essence, by the beginning of the 20th century, scientists saw the universe as a giant, complicated mechanical device. Kind of a supersized version of this orrery. The idea was that the universe is a huge and intricate machine that obeys orderly mathematical rules. If you knew the rules of how the machine was configured to start with, as you turned the handle over and over again, it would behave in an entirely predictable way. If a nice mathematical system that worked in a similar way to my orrery, scientists assumed some malign outside force was causing it. The man who forced the scientific community to confront it was an American meteorologist called Edward Lorenz. In the early 1960s, he tried to find mathematical equations that could help predict the weather. Like all his contemporaries, he believed that in principle, the weather system was no different to my orrery. A mechanical system that could be described and predicted mathematically. But he was wrong. When Lorenz wrote down what looked like perfectly simple mathematical equations to describe the movement of air currents, they didn't do what they were supposed to. They made no useful predictions whatsoever. It was as if the lightest breath of wind one day could make the difference a month later between a snowstorm and a perfectly sunny day. How can a simple system that works in the regular clockwork manner of my orrery become unpredictable? It's all down to how it's configured, how the gears are connected. In essence, under certain circumstances, the tiniest difference in the starting positions of the cogs, differences that are too small to measure, can get bigger and bigger with each turn of the handle. With each step in the process, the system then moves further and further away from where you thought it was going. Lorenz captured this radical idea in an influential talk he gave called "Does the Flap of a Butterfly's Wings in Brazil Set Off a Tornado in Texas?" It was a powerful and evocative image, and within months, a new phrase had entered our language: the butterfly effect. It seemed unpredictability was hardwired into every aspect of the world we live in. The global climate could dramatically change in the course of a few short years. The stock market could crash without warning. We could be wiped from the face of the planet overnight, and there is nothing anyone could do about it. Scientists realized that there was an unexpected link between nature's power to self-organize and the chaotic consequences of the butterfly effect. Complex and unpredictable natural systems can emerge from surprisingly simple mathematical rules. These rules have a unique property often referred to as feedback. This screen behind me is connected up to the camera that's filming me. But the camera in turn is filming me with the screen. This creates a loop with multiple copies of me appearing on the screen. This is a classic example of a feedback loop. We get a picture in a picture in a picture. At first it seems fairly predictable, but as we zoom the camera in, some pretty strange things begin to happen. The first thing I notice is that the object I'm filming stops bearing much resemblance to what now appears on the screen. Small changes in the movement of the match become rapidly amplified as they loop round from the camera to the screen and back to the camera. So even though I can describe each step in the process mathematically, I still have no way of predicting how tiny changes in the flickering of the flame will end up in the final image. This is the butterfly effect in action. But now here comes the spooky bit. With just a slight tweak to the system, these strange and rather beautiful patterns begin to emerge. The same system, one that's based on simple rules with feedback, produces chaos and order. But one scientist, more than any other, brought a fundamentally new understanding to this astonishing and often puzzling idea. His name is Benoit Mandelbrot. Underlying nearly all the shapes in the natural world is a mathematical principle known as self-similarity. This describes anything in which the same shape is repeated over and over again at smaller and smaller scales. A great example are the branches of trees. They fork and fork again, repeating that simple process over and over at smaller and smaller scales. The same branching principle applies in the structure of our lungs and the way our blood vessels are distributed throughout our bodies. It even describes how rivers split into ever smaller streams. And nature can repeat all sorts of shapes in this way. Look at this Romanesco broccoli. Its overall structure is made up of a series of repeating cones at smaller and smaller scales. Mandelbrot realized self-similarity was the basis of an entirely new kind of geometry, and he even gave it a name: fractal. What I'm about to show you is one of the most remarkable mathematical images ever discovered. Epic doesn't really do it justice. This is the Mandelbrot set. It's been called the thumbprint of God, and when we begin to explore it, you'll understand why. Just as with the tree or the broccoli, the closer you study this picture, the more detail you see. Each shape within the set contains an infinite number of smaller shapes, baby Mandelbrots that go on forever. Yet all this complexity stems from just one incredibly simple equation. This equation has a very important property. It feeds back on itself. Like a video loop, each output becomes the input for the next go. This feedback means that an incredibly simple mathematical equation can produce a picture of infinite complexity.
The really fascinating thing is that the Mandelbrot set isn't just a bizarre mathematical quirk. Its fractal property of being similar at all scales mirrors a fundamental ordering principle in nature. Complex systems can be based on simple rules. That's the big revelation. Design does not need an active, interfering designer. It's an inherent part of the universe.
So we've seen how two of the major pillars of physics, thermodynamics and chaos theory, explain so much about the structures of life and the basic laws that underpin it. But in recent years, and this is an area I've personally become involved in my research, it's been realized that quantum mechanics may also play a role in explaining some of the most important mechanisms of life.
As we saw in the previous episode, the behavior of subatomic particles is completely baffling. They behave as though they're smeared out in space. They pop in and out of existence all the time. And you can only express their location and movement in terms of probabilities, not certainties. But for decades, no one had any idea that the Alice in Wonderland world of quantum mechanics could be important in the realm of biology. In recent years, that's changed. Quantum biology is a growing branch of science. And at the University of Surrey, my colleagues and I are heavily involved in pushing back its boundaries. We think spooky quantum effects may play an important role within living organisms. I'd like to show you an example, a bizarre process called quantum tunneling. When physicists say you have to put in effort to get something done, we have a special term for it. We say you have to overcome an energy barrier. I want to look at quantum tunneling because it's an extraordinary way in which particles can move, enabling them to cross energy barriers, barriers which are even more challenging than the walls of a medieval castle. It all revolves around another strange fact from the world of quantum mechanics. Particles can cross barriers in a very spooky way indeed. They act like ghosts.
I wouldn't blame you for thinking that this is an idea that a clever theoretician has come up with, that it's just mere speculation, something that we have no proof of. But we do. It takes place all the time.
In the quantum world, protons don't have to go over barriers. They can tunnel straight through. A quantum particle can tunnel from one place to another, even if it has to pass through an impenetrable barrier. In nuclear physics, this effect is a proven fact. The most important advantage of tunneling is its speed. It happens incredibly quickly, much faster than if protons go over the barrier. As a nuclear physicist, quantum tunneling is my bread and butter. Subatomic particles like protons do it all the time. But what has this got to do with biology?
At the University of Surrey, we're currently researching whether quantum tunneling is involved in the central process which propagates and diversifies life on Earth.
You'll probably recognize this as the famous DNA double helix. discovered by Crick and Watson in 1953. This molecule contains our genetic code. It's the instruction manual for all life on Earth. The double helix structure is stable. It's like a twisted double spine, like a twisted ladder. But it's the rungs of the ladder that are of interest to me. They're made up of 4 smaller molecules called bases: adenine, thymine, guanine, and cytosine. And these bases fit together in a very special way, like pieces of a jigsaw puzzle. So the 2 strands fit together when guanine fits to cytosine and adenine fits to thymine. But every now and again, mistakes take place, and understanding how and why they happen is incredibly important.
The evolution of all living things depends on DNA mistakes, known as genetic mutations. Sometimes a mutation might give an organism an edge in their environment, and they can reproduce more efficiently over very long timescales. That's how species change. But how do these mutations occur? Let me take you through a hypothesis we're currently researching.
Here's a computer simulation produced by my PhD student, Max. In the foreground, you can see the DNA double helix in colour, and the grey blob in the background is the helicase. Now, that's an enzyme that splits the 2 strands of DNA apart so that each can then make a copy of itself. Now, if we zoom in, we can see the bases all linked together inside the DNA, but we get into the business end. So down at the molecular, at the atomic level, the green is guanine and the yellow is cytosine. These 2 bases that are held together by hydrogen bonds like this one, which is basically a proton. So now we're down at the quantum realm, which of course is my specialism.
It's this subatomic bonding of the bases which most interests me.
Now, these protons spend most of their time on one side, but every now and again they can jump across to the other side. However, they just jump back again. But if the 2 bases split with the protons in the wrong positions, then that changes the shape of the bases. Now, when the strands of DNA make copies of each other, green would normally fit with yellow. However, now they can't. They're like jigsaw pieces that don't fit together. But if an orange comes along, green can fit to it. However, this shouldn't happen. Green shouldn't fit with orange. This is a mistake.
Now, of course, you can guess how we think the protons jump. We think quantum tunneling is happening inside DNA. Which means it could be one cause of mutations. I'm working on this theory with Professor John Joe McFadden.
Mutation can be caused by many different phenomena. Radiation causes mutation. Ultraviolet light causes mutation. So there are many mechanisms of causing mutation, of which the proton moving from one place to another is one of them.
If it is the moving proton that causes mutations, it could find its way across the energy barrier, not by quantum effects, but what we'd call ordinary Newtonian physics.
The question is whether they move by classical ways, like a snooker ball moving from one place to another, or whether they move by quantum mechanical means in which they essentially disappear from one position and appear at another.
Our preliminary results look very promising.
The recent work of our students then has revealed if it moves at all, it moves quantum mechanically. If the proton moves from one place to another, it's doing it as a quantum mechanical particle.
It's possible this might even have far-reaching consequences in the medical world too.
And of course, mutation is responsible for evolution, but it also has a bad side. It's responsible also for making cancer cells cancerous. Cancer is caused by mutations. Single molecules have macroscopic effects. They change us. And mutations in single molecules can mean the difference between life and death.
It's very exciting to me to think that the great pillars of physics, thermodynamics, chaos theory, even quantum mechanics, are being used to help us understand the ordinary natural world around us.
Now I want to end this film by looking at one of the greatest mysteries in all of science. How did life itself begin?
Let's think ourselves back, perhaps 4 billion years, to a primeval Earth, with simple chemicals in a rock pool and energy flowing in from a thermal vent. It's one of the great outstanding mysteries of science. How did simple chemicals become the complex forms we know as life? It's not often realized that the underlying principles of life come from the laws of physics, such as thermodynamics. I can even show you the basic principles in action with a simple little backyard experiment.
Now, all I've got in this pan is some silicon oil. There's a bit of mica powder in there, but that's just to add color. A physicist or chemist would say that until I put it on the stove, there's no energy going in or out. And of course, it has no structure to it. But as soon as I heat it up, hopefully some interesting things will happen.
Quite rapidly, these shapes appear. They're known as convection cells. They formed because the bottom of the oil has suddenly become very hot. The system has lots of new energy pouring into it. And as the heat dissipates through the system, ordered symmetrical structures spontaneously appear.
These pretty convection cells are a classic example of something we see again and again in the physical world. They're called dissipative structures.
It's worth remembering that this isn't a chemical reaction. All that's happening to this oil is that heat, energy, has been pumped into it. Some scientists think understanding the flow of heat through dissipative structures is key in understanding the development of life. Recently, an experiment was carried out by a team of scientists in America using these little robots called smarticles. Switch their batteries on and all they can do is flap their arms about. So generally they just crash about randomly. It's all a bit of a mess. They're acting individually and the whole system is chaotic and unstable. But then the scientists programmed these smarticles to move their arms in a more predictable up and down way. Quite quickly, this collective behavior spontaneously emerged, almost like synchronized swimming. These smarticles look like they've been choreographed, yet they haven't been programmed to join up or to cooperate in any way. They just self-organize into regular patterns, even leading each other in a little orbit around the ring. The scientists realized the smarticles were somehow choosing the structures which would enable them to stay stable and avoid being knocked around by the patterns of energy flowing through the system.
They discover these dances, these kind of organized collective behaviors, because this is the way that they can work together so that the energy flowing through them doesn't disorder them and just kind of maintains them in that state.
So the idea being explored is that on a primeval Earth, chemicals encountering a predictable source of heat may have entered a feedback loop, changing their shape to become more stable as the energy flowed through them.
One of the properties of living things is that they are able to maintain themselves in this specialized state only because the energy flowing through them has a very particular pattern to it, and that they've kind of adapted or emerged even in the presence of that kind of pattern. So it's an evolutionary process then.
In effect, it's a kind of natural selection process, favouring the combinations of chemicals that find the most stable form. Ideas like this may help us fill in a huge gap in our understanding of how life developed.
I think that sometimes people have a tendency to kind of imagine that before there's life, you just have random mess, and that you need a completely unimaginably unlikely coalescence of recognizable lifelike structure out of absolute vacuum, so to speak, out of nothing that looks like that at all. And this is about how I think the physics helps you to maybe fill in a gray spectrum between that extreme inchoateness on the one hand and something that you'd call life on the other, where in between there's a lot of lifelike emergence that you can argue for.
So could it be that the physical laws of the universe actually make life more likely than we've previously imagined? It's clear that science is starting to get to grips with some of the greatest mysteries of life.
Here's a philosophical question for you. Where do you draw the line between life and non-life? I think we can all agree that fire isn't alive, and yet it has a lot in common with life. It needs energy, heat, to survive, by burning fuel in the same way that we burn calories. It can create beautiful transient patterns, and it has the ability to reproduce itself.
So at what point did non-life become life? At the University of Glasgow, a major project is underway to try to actually create life in a lab. Professor Lee Cronin and his team have built a series of chemical computers called chemputers. This is Genesis engine number 1, Genesis engine number 2, and there's a series of other origin of life machines. The machines are designed to gather together the simplest molecules which might have been found in a rock pool on a primeval Earth, such as carbon dioxide and methane, adding methanol and water, and then driving heat through them. Then the scientists study the molecules as they combine and recombine through cycle after cycle.
Now, what are we looking for? We're looking at molecules that are growing, getting bigger, molecules that are related to one another. Maybe they have the same, almost the same identity, but a bit different. And because then that would be what we see when we see evolution starting, as the molecule parent makes a slightly different child, but you can see that they're related and they carry on going.
Lee believes any theory of life has to be based on information, because at the most fundamental level, it's information that describes complex systems and which is necessary for things to evolve and change.
Probably life didn't really emerge in chemistry, it emerged in information, and chemistry just happened to be the substrate that carried it.
He's working closely on this idea with theoretical physicist Professor Sarah Walker.
So I'm working with Lee on some of these ideas because I had this kind of drive to develop a theory for what life is, which is really based on this concept that somehow information is going to be playing a critical role in what we might call the physics underlying life. Objects like you and me, the cup, the Zoom, complex molecules like proteins and things, all of those things require information or an evolutionary process to create them in the universe, and that's the physics we want to understand. How does the universe spontaneously generate information and information processing systems that then undergo this process that we call evolution and build all the complexity that we see in the world?
This is thinking on the grand scale, not just the origin of life on Earth, but everywhere in the universe.
My mission in science is to basically come up with the plausible scenarios that would give rise to the origin of life on Earth. But actually, who cares about that? It's like saying we want to understand the origin of our sun. But when you look in the sky, there's suns everywhere. So what I want to do, if this works, I'm not going to work out what did happen. I'm going to be able to work out what does happen. My very strong belief, it is a belief, and but what I'm trying to do is test this belief, is that life is everywhere. So by understanding the origin of life and making life now, we will be able to statistically map how life works in the universe.
One of the reasons physics hasn't been able to explain life yet are concepts of what the theories need to look like are just not structured properly yet. And we haven't been creative enough to think about breaking free of the mold of physics as it's been done in the last 300 years and invent new ways of doing it to address the problems that are in front of us now, like what is life? What are minds and consciousness? How does intelligence evolve over planetary scale timescales? What other things like us might exist in the universe?
Right now, life on Earth means nothing if Earth gets obliterated and we don't affect the rest of the universe. So my ambitions, Nobel Prize, that's too low an ambition. The ambition is to create a technology that we could seed the universe to transmit our origin of life idea and create other living worlds where there were none. And I can imagine us having an ethical debate in the future when we know how to do this, to say, is it ethical to infect this planet with an origin of life scenario? Are we going to destroy the life that's on the planet? Is the planet definitely dead? So my ambition is to make sure that we find life elsewhere in the universe, understand life on Earth, and if there's not life elsewhere in the universe, we better make sure that we make the most of our universe by making sure life escapes Earth.
As we've seen throughout this series, today's generation of scientists are pushing back the boundaries of what it's possible for us to know at a breathtaking rate. I believe that as a human race, we should take pride in our achievements, that science is at the threshold of answering the deepest questions of existence. And for me, physics is the true path to understanding the nature of reality. And with that understanding, we can shape our world and our destiny.